Okay, so good afternoon, everyone, and welcome to another colloquium of the Valongo Observatory. And today I'm very pleased to present our own Arianna Cortesi, who is currently a postdoc in our institute. And so that you know, Arianna has a PhD in astronomy from Nottingham University. Then she did a postdoc at the University of São Paulo at the Astronomy Institute there. And she has been a postdoc in our university, in our institute, for a little over 2 years now. And Arianna works in a number of topics related to galactic and extragalactic astronomy, with emphasis on planet nebulae, globular clusters, galaxy formation, and in particular, galaxy morphologies as well. And Arianna is going to talk to us a little bit about her work on galaxy morphologies. Today, as you might have seen in the announcement, the title of the talk is Galaxy Morphologies in Multiband Surveys, the Narcissism of Little Differences, which is a very interesting, very interesting title. I'm very curious to see and to hear how galaxies are narcissists. But thank you very much, Arianna, for accepting our invitation and for being here. And I'll leave the floor to you now. Thank you very much.
Okay, thank you, Tiago. So I hope you can hear me well. And as Tiago was saying, I am now a postdoc at the Observatory of Valongo, and I'm part of LASEX team. And I am collaborate with several people, and that I list here, some of them. And I'm part of S+, J+, and Kanga collaboration. So this image I've chosen as a first image is an image that shows how morphology of objects can tell us about the life that the galaxy or a person has gone through. So when we look at the morphological sign, we can understand what happened in the life of the object in study. Okay, so I will first speak a bit about galaxies morphologies. Then I will present the JPAS survey and some preliminary results that we obtained for galaxies morphologies using mini JPAS data. Then I will speak a bit about S+, and I will present some results from S+ survey, and I will conclude speaking about N3115 and the need of using more than optical data to properly recover galaxies' morphology and their stellar population. So, as we know, galaxies present different morphologies. This is the Hubble Galaxy Classification Scheme, and it presents elliptical galaxies on the left side, which are round and generally red. And on the right side, we have spiral galaxies that can have or not have a bar. So we have bar spiral in the bottom and unbarred on the top. The irregular galaxy are on the far right of this plot. And then we have a transition of morphological types that present different ellipticities, different number of spiral arms, and something I'm very interested in are the lenticular galaxies or S0 galaxy that lie at the apex of this diagram, having a morphology that is a mix of the two. So when we look at morphology, we can also try to connect morphology and kinematics. This is from a work of Falcón Barroso 2015, where he compared the lambda parameter, that is a proxy of the ratio of the rotational velocity in a galaxy and the dispersion velocity in the galaxy, with the ellipticity of the galaxy itself. The dots here show different Hubble type, going from red that are elliptical to spiral that are blue. And the location of the object in this plot can tell us if they are fast or slow rotators. So on the bottom, near the red objects in squares are called slow rotators. They are generally elliptical galaxies and they are dominated by dispersion velocity. On the contrary, the rounder symbol represent fast rotator. Fast rotator, as is possible to see, show different morphological type from elliptical to spiral, being the spiral galaxy on the top right of this plot having high lambda and high ellipticities. Also, it's possible to connect galaxy morphology to the stellar population of a galaxy. This is a work from Kavin Shambinsky et al. 2014, where he presents different galaxy type for different color and stellar masses. So stellar masses is on the x-axis and color are on the y-axis. And it's possible to see that galaxies fell in three different groups that are called red sequence, the green valley, and the blue cloud. Actually, the green valley is a region of transition between the red sequence and the blue cloud. Early type galaxies tend to live in the red sequence and in fact are generally dominated by old and metal-rich stellar population, while late type galaxies tend to be bluer and have occurring star formation in their disks. Now, morphology, as we were saying, holds clues of the galaxy formation history. As we can see in this beautiful deep image of NGC 5866, it's possible to see all the passages, for example, of small companion around the main galaxy of the system. But morphology can be misleading. In fact, this is the same galaxy seen from the Hubble Space Telescope, which still has an exquisite definition and depth, but yet we cannot see anymore this accretion around the galaxy. And finally, this is the same galaxy seen from, I think, SDSS data. So it's possible to see how much depth and resolution of the image influence our ability of understanding the morphology of the galaxy. So I've chosen this title because when I started working with JPass data, I realized that JPass data, as we will see in a moment, are composed by several narrow bands in the optical wavelengths. So the difference between a galaxy image in every narrow band might not be so strong, but yet we could infer a fundamental understanding of the galaxy type and stellar population given this filter system. So the narcissism of small differences is a phrase that Sigmund Freud defined to exactly speak about the obsession that sometimes people have in neighboring villages in finding differences among what they do, for example, food, when the same food seen from somebody far away could look exactly the same. So what I want to discuss with you today is what can we learn from having these multi-band surveys. Okay, so JPass survey is a survey that uses telescopes that is in Teruel in Spain. Actually, there are two telescopes there, JPCAM and the J plus T80 North telescope. And this is an image of the beautiful place where the two telescopes stands. And JPass aim to cover 8,600 square degrees in 56 narrowband filter plus 4 broadband filters. And it tends to be almost an all-sky IFU survey given the definition of the narrowband filters and the is all good? And I'm sorry. So, given the definition of the filter system and also the depth of the images, its main objective is to measure BAO up to a redshift of 1.3, but it can be useful for several research topics, including studying galaxies evolutions. Okay, this is a drawing of the telescope, which is 2.55 meter and a field of view of 3 square degrees. And this is an image of the telescope as it is standing now. The filter, the CCD system is very optimized to be able to cover the whole sky with these 56 narrowband filters, having a system of 14 CCDs and 4 trays of narrowband filter and 2 trays of broadband filters. And this is the JPass filter system, where it's possible to see all the 56 filters that makes it a unique filter system. So a first data release have been obtained by observing the ages field as shown in this picture in the mini JPass survey, as it is called, since before the JPCam was installed, another camera was used to acquire data using the same filter system in order to understand what we can do with this type of data. So these results are published in Bonoli et al. 2020 work, and it's possible to see on the right the quality of this data in RGB images. So the image in the center just mirror the image on the left, where it's possible to see the fourth field of view. And the 3 rectangle ABC are zoomed in regions of this combination of the 4 observation, of the 4 fields observed. We have chosen 2 galaxies to be used as test cases to understand our ability of recovering galaxy morphologies using JPass data, a lenticular galaxy on the left and a spiral galaxy on the right. And we are using 3 methods to do so. We are using Morphometrica, that's a code published by Ferrari et al. In 2015, and that keeps being updated from his work and his student work. And then we use Curvature, a code developed by Lucatelli and Ferrari in 2019. And finally, we use Megamorph, a code that is an extension of Galfit to multiple band fitting. I'm gonna now go through each one of these, giving an example. So Galfit M, as I was saying, expands a Cercic profile, which is a parametric function to fit galaxy light through wavelengths. So you can see here the equation of the Cercic profile, where the intensity is defined in function of the radius, and it's possible to see that we have a central surface brightness, EA, and then we have the effective radius, RE, and the Cercic parameters, N, all expanded for wavelengths using Chebyshev polynomial as shown in the equation on the top. It is possible to define the degree of freedom with which parameters vary through bands, as we are going to see in a moment. And it's possible to go from having no freedom and so fitting the same quantity through all bands to linear relation to a quadratic relation and so on. So in here, I'm showing the result of running Galfit M on the lenticular galaxy. So the first 56 squares represent the galaxy image in all the different bands. It's then possible to see the model of the galaxy and the residual obtained by subtracting the galaxy image for the model of the galaxy light. And we were quite happy with the residuals. So we went on using the result of this fit, where we fitted a bulge and a disk, and the companion galaxy, as is possible to see. Morphometrica recover instead what they're called generally CAS parameters, that are concentration, asymmetry, smoothness, entropy. This is a non-parametric approach to the analysis of galaxy images, and it's possible to see here the result of Morphometrica for the same galaxy. They are written in text. And it's possible also to see that Morphometrica recovers a single Sersic fit, that's the model in the image, shows the residual, and also several maps of asymmetry and smoothness. And something that's very interesting is the polar map that show the variation of somehow is a way of mapping the presence of spiral arms and bars in an image. Finally, we're using curvature, which is a way of measure the intensity of the light profile and finding the places, the region of the galaxy where the light profile changes, as shown in this image, where the curvature is on the left, on the y-axis, against the radio normalized for the Petrosian radius. It's possible to see that when we take the first derivative of the galaxy light profile, which is in red, we get the curvature, and the peak of the curvature defines the region in which there is a change in the galaxy light profile, which can be associated to the transition from the bulge to the disk region inside the galaxy. And what we are trying to find is a way to use this method to define the value for the inner and outer component of the galaxy fit, to be used in a second moment also to define the initial parameter of GAFT M. So in here it's possible to see that if we just plot the same curvature as before, it's possible to show the inner part of the light, the outer part, and to define the radius where we have 50% of the light of the inner component and 50% of the light of the outer component. And in this final plot is shown the ratio between the effective radius of the bulge and R50 obtained through curvature, for and the same for the disk in the plot on the right. And as you can see, on the x-axis are the wavelengths, and on the y is the ratio between the two, and the ratio is generally quite nearby 1. So the method seems to really be able to recover the same parameters as a Sersic and an exponential profile fitting. So when we combined all this data to try to understand what we can find for galaxies using the mini JPass data, we join all this information in this plot that I'm showing here. So on the left side, it is just shown the image of the galaxy in different bands for the elliptical lenticular galaxy on the top, for the spiral galaxy on the bottom, and the two color images respectively. And on the right is a plot that shows the variation of the concentration C1, that is a measure of the inner concentration, versus wavelengths, versus lambda, for the spiral and lenticular galaxy, color-coded according to the bulge to total light ratio that we obtained from Galfitan fit. It is possible to see that while the concentration is nearly constant for the lenticular galaxy through wavelengths, it varies for the spiral galaxy, being lower for bluer wavelengths and higher for redder wavelengths. This is expected because somehow it's showing the transition between the bulge, so in the redder wavelengths, and more concentrated region, to the outskirt that is bluer and disk-like. And disk-like. Also, when we look at the bulge over total light color, it's possible to see that in both galaxies there is a variation of this parameter through wavelengths, and is something we're still exploring, but it's very interesting to see that, for example, for the lenticular galaxy, B over T is higher for the bluer component than for the redder component, which is something not expected. Finally, what we aim to do in collaboration with Paola Di Mauro and other people in JPass is to perform an SED fitting of the bulge and this component. So in here we plot the magnitude versus wavelengths for the disk component in blue and the bulge component in red, as recovered with GalFitM. And it's possible to see that we are quite able to obtain a reasonable fit for the sterile population of the two components. And to finalize this part on JPass, I will just refer to two papers that have been recently published for the mini JPass survey. The first one is from Bonnelly et al., which is the mini JPass survey preview of the universe in 56 colors, and the second from Gonzalez Delgado et al., which is the mini JPass survey paving the way for the identification and characterization of galaxy population. Actually, this paper has been accepted by now. And I will finalize showing this beautiful image of Andromeda taken with JPass. Okay, now I'm gonna move to the second survey I wanted to present, which is S+. S+ is the Southern Photometric Local Universe Survey, and it is a twin survey of J+. So S+ uses the T80 South telescope shown here, which is in Cerro Tololo in Chile, which is a twin telescope of the T80 North that is next to JPass telescope. So this is an image of the T80 South and where it is located in the mushroom farm in Cerro Tololo. And this is how it was before the telescope was constructed. So in here I'm showing the area of the sky that will be covered by S+ in comparison with other surveys that are happening in the southern hemisphere. The southern hemisphere is a very exciting part of the sky to study, since yet there is not a survey like SDSS in the north that really covered almost all of the northern sky and characterized galaxies morphologies using, for example, Galaxy Zoo and several other way of defining galaxy morphology. The south hemisphere yet is to be discovered in a sense. And in here I'm showing the area and photometric depth of several surveys in comparison with S+ that is not as deep as DES or Viking or KIT survey, but has actually a very large area in comparison with them. So it's gonna provide a very interesting data set. The DR1 catalog is already public and it covers the Stripe 82 area. This is the filter system that show 7 narrowband filter and 5 broadband filters. The narrowband filters are located in specific feature of stars formation, stars emission and absorption. And here is an image of the Hydra cluster taken with S+, which allow us to understand the quality of this data. So it's shown the 1.4 square degree field, and then a zoom in that allow us to understand the quality of this data when we go deeper and deeper zooming in. In here I show the depth of the survey for different signal to noise for the G and the R band. So it's possible to see that for a signal to noise of 5, for example, the survey reached a depth of 20.88 in G band and R band. And then, of course, going to a higher signal to noise, we go to lower magnitude limit and vice versa. And here is the same idea where we look at the completeness of the survey for different magnitudes and redshifts. So depending of the error we allow in the estimation of the redshift, we get different completeness as well as different ability completeness for redshift. And here is an example of different type of objects as seen with the plus. So it's possible to see, for example, that it's possible to characterize planetary nebulae and symbiotic stars, given the H alpha filter combined with all the other filter. It's possible to look at galaxies and star SED, and also at QSO. Now, going toward the morphology specifically, these are results of a work led by Claes Gibbon, where we tried to characterize galaxy morphology in stripe 82, observed with this plus, using deep learning methods. These two plots shows our data, their magnitude and redshift distribution, spectroscopic redshift distribution, and they are divided in three classes because we use Galaxy Zoo to train the deep learning method. Galaxy Zoo has a full catalog and a debias catalog. The debias catalog is a catalog where objects for which the obtained morphology was really uncertain have been removed. And so these allow us to have three catalogs. One, that the one that was used for training and validation, that is the ones that match the Galaxy Zoo debias catalog. Then we have a second catalog, which is the one that has the ambiguous galaxies, that are the ones that are removed in the debias catalog. And the third one that contain galaxies that are not present in Galaxy Zoo dataset. It's possible to see anyway that the distribution of magnitude is very similar, even if there are more galaxies, more faint galaxies at in the second group, which is expected because the fainter the galaxy, the harder to understand if the presence of spiral arms. And the same with redshift. It's possible to see that the first redshift pin contain mostly class 3 objects. In fact, Galaxy Zoo data, in order to be respectful of the richness of galaxy in the universe, don't take very nearby galaxy because are not representative of the cosmological volume. This is an example of the 12 images of an elliptical and a spiral galaxy in S+, and the GRI color image. So it's possible to see that going toward redder bands, the signal to noise increases for both the elliptical and the spiral galaxy. And it's possible also to see that the spiral arms are well defined in the bluer bands. In here, we compare the classifications that we obtained with classifications from Dominguez and Sanchez 2010 that also used deep learning method starting from Galaxy Zoo 2 data, and Nair et al. That instead use a visual morphological classification. I'm going to start from the plot on the left. So Dominguez and Sanchez provides the T-type of the galaxy, which is a number that tells us the morphology of a galaxy. More or less, T-type lower than 0 are elliptical galaxy. Lenticular galaxies tend to be between -3 and 0, while spiral galaxies are higher than 0. And as you can see, in red and blue are the histogram representing the distribution of the elliptical galaxy as classified in our work and the spiral galaxy. It's possible to see that the two classification really match well. So where we have that the peak of elliptical galaxies is for a T-type of minus 2.5 as expected, while the peak of spiral galaxy is between 4.5 and 5, depending on which of the three subgroup we are studying. Reminding that 1 is training and validation, 2 is the ambiguous class, and 3 is the blind sample. When we look at the visual classification from Nair et al., again, we see a nice match between our classification and Nair et al. Classification. I think it's very interesting to look at the middle panel of the comparison with Nair et al., so on the right, where it's possible to see that the region of confusion is mostly where lenticular galaxies are. And that's because it's very hard to distinguish a lenticular galaxy from a spiral galaxy when the definition of the image decreases, as in the ambiguous class, since it's very hard to see the spiral arms, which are the main cause of difference in the classification. And here is an example of galaxies classified as elliptical and galaxies classified as spiral with different probability. So prob 1 means that we're almost certain they're spiral or we're almost certain they're elliptical, and lower probability starts saying that we are not so certain. It's interesting to see that the galaxy with the highest probability are not the biggest one, and that because this size of galaxy are the most typical of the data set, and so somehow that leads them to be also the most probable. And I will finalize some example of this work by showing this plot that link us with the next one, where we show the distribution of galaxy in the C2 H plane. So C2 is concentration of the galaxy as recovered from with Morphometrica, and is a measure of the outer part, let's say concentration, and H is entropy, which is somehow a measure of the clumpiness of a galaxy. So spiral galaxies will have a higher H than elliptical galaxy, and elliptical galaxies will be more concentrated than spiral galaxies because these objects have a lower value of concentration. And again, we have these for the class 1 object, so training and validation, 2 that is ambiguous, and 3 that is a blind sample. And if we look at the training and validation, we can see that we are really able to separate the galaxies using concentration and entropy in the elliptical and spiral group, or looking in the other side, the elliptical and spiral classification we made has full sense when we look at it in this plane, because the two set of galaxies show different morphometric properties. So as I was saying, this plot leads to the next one, which is a work that Locatelli is leading to recover lenticular galaxies. So before we were focusing only in elliptical and spiral galaxy, and now we are trying to add the lenticular galaxy class to the game. So in this plot is shown concentration in the case C1, which is the inner concentration, versus K median, that is a median value of the curvature of each galaxy. Class 1 are elliptical, class 2 are spiral, and class 3 are at 0. So elliptical are blue, spirals are red or orange, and zeros are green. It's interesting to see that how expected, if we think about that, the Hubble classification scheme, lenticular galaxies tend to be in the middle between spiral and elliptical galaxy. But yet it's interesting to see that these two parameters somehow allow to separate them into a third class. So stay tuned, that soon more results will come out. And if you want to join the S Plus team, is just to contact Claudia Mendes de Oliveira, that is the PI of the survey. And I will conclude speaking about NGC 3115. This is a work that has been recently accepted in monthly notice, and the first author is Maria Luisa Busto. And so NGC 3115 is the closest galaxy to the Milky Way, the closest lenticular galaxy to the Milky Way. And it's a very interesting galaxy because it's isolated, which is quite atypical of lenticular galaxies that tend to be found generally in cluster or in group, but in denser environment. Since there is a strong link between lenticular galaxy and galaxy morphology in general and the environment. We decided to study this galaxy in particular because being isolated, we kind of decrease the number of formation mechanisms that could lead to the formation of this galaxy. Since, of course, it cannot be ramp pressure stripping or other type of mechanisms that are typical of a cluster of galaxies. And we decided to use all the data we could find in the literature, or almost all the data we could find in the literature, to describe the full SED of the galaxy. So going from the far UV to WISE data at 4.6. So the first row of this table shows the input image that we gave to Galfit M to perform then a single Cersic fit, a bulge to disk fit, and a bulge and two disk fit. The images are FUVI and UVI from Galax, GRI from Subaru, the Z bands is from DICAM, then GH and KS is from Tumas, and as I was saying, the last two are WISE data. Then we have the model for the single Cersic fit in the second row, and the residual. Then in the fourth row, we have the model of the bulge disk fit and the residual, and finally the model of the bulge and two disk fit and the residual. In the last three rows, we show the result, how the three components of the bulge and the two disk fit look like in all bands. And as you can see from the residual, and if you want more detail, I will refer you to the paper, it's possible to see that the bulge and two disk fit is the fit that mostly allow us to remove all the light of the galaxy and better recover the galaxy light profile. Of course, when you look at this residual that are in the seventh row, it's possible to see that even so, we have residual in the image, and these residual are linked to the presence of an end-on bar in the center of the galaxy, most probable, and two tiny spiral arms fading away or just reborn. And what I think is very interesting as a result of this work is that it shows us how important it is to complement the optical and data with infrared and UV data. In fact, when we look at the plot on the right, where we have different color versus radius, it's possible to see that the galaxy color vary depending from the wavelength range we are using. And we can see, for example, that the nuvi minus R and FUVI minus nuvi color tend to increase with radius, while an opposite trend is seen for the optical and infrared colors. In here, the difference between the green and the blue line is that the blue line comes from using the model of Galfitam to recover the color, the model image, while the green line show what the color we get using the image itself. The red line shows effective radius of the bulge of the galaxy, and the yellow dot line show where this component becomes dominant over the bulge component in the galaxy. I think it's very interesting to see that in the G minus R and R minus I case, this radius seems to be the radius where we have a turn in the color. And so what we conclude by looking at this data is that the center of this galaxy has a bluer stellar population than its outskirts, and this bluer stellar population is not caused by the presence of an AGN, as it was shown by running an SED fitting. And with great joy for us, this paper has been published in Astrobytes yesterday. Okay, so I will conclude now speaking very briefly of Kanga. Kanga is a census of Austral nearby galaxy led by Karin Menendez del Mestre. And we have brought a proposal for SOAR focused on lenticular galaxies. So Kanga is a project that aims to obtain deep optical images of galaxies that have Spitzer data in order exactly to be able to study the full SED from optical to infrared data in order to properly recover the galaxy stellar population. And in this case, we have focused on lenticular galaxy for this proposal. The proposal has been accepted, awarded 30 hours. Then, unfortunately, during the observation, due to bad weather, we couldn't observe all the galaxies we aim to observe. But here are shown some of the examples of the galaxies we were observed inside a circle that represents the field of view of SOAR. So this image already shown how different lenticular galaxies or galaxies classified as lenticulars can be. And so soon we will be able to give you more results also from this work. And I will finalize my talk by speaking very briefly about astronomy as a tool to make a better world. And there are several projects I am involved with. One is called Under Other Skies, Dialogues of Different Cosmological Paradigms. That's a project that want to record chants of an indigenous population, Mashakali, in the north part of Minas Gerais. And the second project is a project in Italian, which wants to record again stories of cosmic comics. That's a very famous book of Italo Calvino, to present astronomy in a funny way to the world. And the stories of Italo Calvino are then commented by astronomers in order to contextualize them in the real actual astronomical context. And they are a COVID-19 project because it's a project made exactly thinking at people locked up at home. And finally, the third project is a project that is done in collaboration with the Observatory of Valongo. It's called Orumbia. The PI of the project is Gracie Mary. And is a project that is done in collaboration between the Observatory of Valongo and Casa da Cia Siapa, which is a center for that defend and preserve the African heritage here in Rio de Janeiro and in Brazil. And the next event of Orumbia will be on the 15th of May. So if you are interested, please contact me or just have a look in the webpage of the Observatory of Valongo, where you will find more details. And I'm gonna thank you a lot for your attention, and I hope it was clear, even if there is a lot of noise where I live. and I take questions.
So thank you very much, Arianna. And we do have some questions here already. Let me remove this, but let me know if you want to put the slides back on. We can do that. So we have a question here from reminding everyone, if you want to ask more questions, go ahead. I'm reading the comments here, so feel free to ask more questions along the way. But we can already start with Karin's question, and she's saying, "Beautiful work, Arianna. When you show the change in concentration index for spirals and lenticulars, it makes sense that the more prominent bulge in radar bands brings the CI value up." And then she asks, "Why is the concentration index curve so flat for lenticulars? And two, I didn't catch by your mention of the trend being different for radar components or something like that. Could you comment?"
Yes. So, as I was saying, somehow the concentration is higher. I hope I said it is expected to be higher for early type galaxies and lower for late type galaxies. In fact, concentration is somehow similar to the Celsius index. So it tells us how the light, which is the light profile in the center of the galaxy. So, for example, an elliptical galaxy, if you think about it, tends to have a higher surface index and a higher value of concentration. On the other side, a disk galaxy tend to have lower value of the surface index around 1 and the lower value of the concentration. When you think about a spiral galaxy, you can imagine that it's made out, as you were saying, of a bulge that could be more or less prominent and the disk. So what happens is that when you move from the radar wavelength that should be describing, in the case of the spiral galaxy, the bulge, to bluer wavelengths that are describing the disk, because imagine you have star formation occurring in the disk, you see that the bluer wavelengths that are associated to the disk have a lower value of C, as well as they will probably have a lower value of N, of static index. And on the contrary, radar bands have a higher value of C, and so because the radar band represent, in theory, the bulge. So that's why you can see this linear increase. On the contrary, when you look at the early type galaxy, this effect is less evident, even if that's something that, for example, differentiates concentration from the curvature parameter. So the concentration, since you don't have this difference between the stellar population of the different components, you don't see such a change in the trend because you estimate more or less the same value at all wavelengths, meaning that the shape of the galaxy tends to be more or less the same at all wavelengths. On the contrary, if you will be looking at the concentration, you might notice that while an elliptical galaxy doesn't have, of the curvature, doesn't have a variation of curvature through radius, it might have a variation of curvature in a lenticular galaxy going from the center where you have the bulge to the disk.
Okay, and Karin is monopolizing the questions here, so we're gonna keep on with her. She also asks about the work by Maria Luisa, and is it possible to quantify how much bigger the bulge looks when comparing different bands? Can you put a percentage to how big the bulge looks in radar bands?
So yes, that's something that will be possible to do, but to do so, you need to allow more freedom in the fitting of Galfitam. So as I was showing, when you set Galfitam for multiple band fitting, you have to choose the degree of freedom with which every parameter changes through bands. And this is not an easy choice to do because more degree of freedom means that The time of the fit can increase toward the improbable value, and also you might not be able to fit the lower signal to noise bands, because somehow when you decrease the degree of freedom with which the polynomial that describe each parameter varies with wavelengths, are somehow using the high signal to noise images to constrain the parameter also for the low signal to noise images. So in the case of 3115, we had chosen to give very low degree of freedom to the fit when fitting three components, because we thought that in the moment you divide the galaxy in three components, you don't expect each component to vary significantly through bands. It will vary in magnitude, but the shape, let's say, of each component should remain almost fixed. So if I remember correctly, we fixed the Cersei index, and we also fixed the effective radius of the bulge to obtain a better fit, which means that the only difference of the fit is actually the flux, so the magnitude of the bulge in all in the different wavelengths, because it's a very interesting point actually to do. That's something we could think about doing, for example, for Kanga, because I thinking when we combine Kanga with the SOAR deep data with the Spitzer data that are also quite deep, we won't need to use such a strong, such a low degree of freedom in the fitting of the parameters. So we could try to quantify this. I hope it's clear.
So maybe Karin is thinking about Kanga as well. Douglas now has a more general question. So, em português, muito obrigado pela apresentação. Poderia falar um pouco da importância das galáxias S0 para entender o atual cenário evolutivo das galáxias?
Yes. Well, there are several recent papers that show that in the nearby universe, lenticular galaxies are the most numerous massive galaxies, which means that understanding how they form means understanding how the most massive galaxies in the nearby universe form. So it's fundamental to understand their formation to understand galaxy formation in general. And there are two important aspects in this. One is that it's very hard to identify lenticular galaxy, because an edge-on lenticular galaxy can easily be misclassified as a spiral edge-on galaxy, and vice versa, face-on lenticular galaxy could really look like an elliptical. Moreover, as I was saying, since the depth of the survey define our ability of recognizing spiral arms, is not so easy to distinguish sometimes lenticular from spiral. Said that, what it has been found by several works like of Coccato and McKelvey et al., and also a work of Evelyn Johnson, recent work, is that you can kind of divide lenticular galaxies in two classes. So one class of lenticular galaxies more massive tend to have an older and more meta-rich population, and they seem to be the result of mergers. So several minor mergers could lead to the formation of a lenticular galaxy. And on the contrary, the lower mass lenticular galaxy should be stripped spiral galaxy, which have a younger stellar population. And if you look at the kinematics, they tend to be more dominated by rotation velocity. And they could be spiral galaxies that either entering the cluster environment or entering the group environment, or for a secular evolution of the galaxy itself, quenched the star formation and became lenticular. I hope I replied.
My apologies. I was on mute here. If Douglas has any further questions, he can ask here. For now, we have a question from Denise, and she's saying, "Thanks for this great talk, Arianna. Does the fact that your method worked better for small galaxies worry you?" And then she follows up a little bit here. For instance, the density of S-type as compared with other works as a function of Z could be affected, doesn't it? And I'll put up another question here. So
it's not that it works better for a low mass spiral. If we would have a universe or a data set that has a lot of high mass big spiral, then they will be the one for which the deep learning method works better. I'm not a machine or deep learning expert, but I think it's not that it works. It's more that it reflects your data set. So if your data set is mostly made of small or medium size galaxies, those are the ones that will dominate the selection procedure, and so are the one for which you get a higher probability of being either elliptical or spiral. And that's simply because the number in general in large surveys, the number of low mass and smaller galaxies, also because they can be smaller because they're further away in redshift, are more dominant. So it's a natural effect, because if you think about it only on a human point of view, like in a visual classification scheme, a big galaxy will be easier to classify because it will be easier to see the spiral arms, it will be easier to see if it's a disk or if it is an elliptical. So that's something, for example, that might differentiate human from computer. Like we are more, we work better with clearer images, and it doesn't matter how many you show us. We will probably always go for the, have a different way for each one to analyze. I'm not sure. On the contrary, the machine learning, since the machine is learning from the data you are giving and doesn't have any previous knowledge as we do, the more numerous objects are probably creating the category that then gives a higher probability. But I can ask Claes as well to comment on this if you wish.
And Edu Teles has a similar question that's going in the opposite direction, I guess, because he's asking, how far beyond the local group can this methodology produce meaningful results, since only 2 arc seconds corresponds to approximately 1 kiloparsec? And he says here local group meaning local supercluster, but mostly. So how far can you actually use this methodology to?
So we usually go till 0.25 redshift, 0.25, 0.3. Now with JPass, we are trying to go even at higher redshift, because the problem again, what limits the method are the data, the quality of the data. So for example, if you work with Hubble, you can do very similar analysis for higher redshift. While with S plus data, I think we are safe in 0.25, 0.3 in redshift. With JPass, we are trying to go further away in redshift, but we already see that when we go at redshift like 3, like we are studying a cluster that's called Amigo 1001 cluster, which I think has a redshift around 3. I'm not 100% sure. But anyway, at higher redshift, the image definition gets toward the limit of the PSF. So when your image is more or less slightly bigger than the PSF, it's extremely hard to run these methods, even probably with the machine learning method. But again, that's something that I don't feel like discussing. But what we see for GalFit-M and Morphometrica is that we are really reaching the limit in which we can fit these images.
Okay, and I think that wraps up the questions that I had here. Everyone is thanking you for your answers. So we have thank you from Karim, thank you from Douglas, thank you from Denise as well. And just to wrap up, we had some other clapping hands here from Edutelis before. Maria Luisa is also watching here. So beautiful talk and congratulations. Amanda also thanks you. And the last thank you I'm gonna put up here is Mariana saying that this will be on her birthday. So apparently that's a plan for her to celebrate. And just to wrap up here, I want to thank everyone who is here watching. So thank you very much. And also if you're watching just the recording of this talk, we will not have a colloquium next week. There are no speakers for next week, but the week after that, in 2 weeks at the end of April, we're going to have Natalia Guerrero from MIT talking about her work with chess and exoplanets. So stay tuned for that, and I'll see you again in 2 weeks. Bye bye, everyone.
Thank you.